further framing the situation, we do a graph of pressure in kilopascals versus volume in liters. We start at state 0, which is here on the diagram. State 1 being here, state 2, state 3, and we come back to state 0. Let's explain what we're doing. State 0, we're at half a liter, 100 kilopascals, 300 Kelvin. Then what did we do? To get to state 1, we heated the gas so that the water would rise in the tube. There was no significant change in volume. We assume a thin tube, and if the tube isn't thin enough, we can make it thinner. We can increase the pressure without changing the volume of the gas significantly by making the tube thin enough. And we do that. We raise the pressure high enough to support the 1 meter column of gas. I was looking for something here. And when we do that, the volume stays constant because we make sure the tube is thin enough, and the pressure rises from 100 to 110 kilopascals. Now, actually, I went ahead and reworked this with more accurate numbers because there's a discrepancy that I will point out when we get to it. Maybe there is no discrepancy. Maybe it's just my imagination, but we'll see where that is. Okay. Now, actually, in state 1, we're not at 110. We're at 109.8 kilopascals, using 9.8 meters per second squared instead of 10 for the acceleration of gravity. And that puts us, instead of 330, at 329.4 Kelvin. So there's a slight difference in these numbers here. So the red numbers are corrections to some of the white numbers here. In going from this state to this state, we calculated the amount of work and did that previously. We got about 12 joules. The accurate is 12.25 joules. Just using the 5 halves and our delta T, this comes out in a very straightforward manner. 5 halves for constant volume expansion of a diatomic gas. And then moving from state 2 to state 3 under the condition that we increase the volume from 0.5 to 0.56 liters, and that is the stated condition. We get to state 2. The temperature, instead of 370, is 368.9. Instead of 110 kilopascals, 109.8 kilopascals, still 0.56 liters. And instead of 24 joules, which was our ballpark estimate, it's 23.05 joules. So there's a slight difference there. Okay? Now, we do the adiabatic expansion, which we just reviewed. There are no joules of energy crossing this the boundary of the system. In other words, the gas doesn't have time to absorb or release heat energy, although it does lose some internal energy to the work done. And we've just seen that. In this state, we have 359.6 kilopascals, 0.599 liters, as opposed to the 360 and 0.6 liters. Very close, but slight differences. Now, we get to the N4 question, I believe, and let's make sure that's right. Okay, the N4 question is, we get to this state after having allowed the water to rise, water to be 60 milliliters of water to flow out, which incidentally increases the potential energy by 0.6 joules, and then release the valve, allow the thing to expand, and we're at this temperature and this pressure. We then simply allow the system to sit in the room at the ambient temperature and cool off. And it'll cool back to its original state, 100 kilopascals, and it'll reduce the volume of the gas to 0.5 liters. That process, we ask what happens, how much work is done, and so forth. So the system actually does negative work during this phase, and loses 36 joules of energy. So, and actually the accurate number is 34.8 joules. 36 joules was an approximation based on approximations of the number of moles and so forth. The 36 joules of heat energy crossing the system would be calculated easily enough. 0.02 moles times about 30 joules per mole Kelvin times negative 60 Kelvin gives us negative 36 joules, calculated in much the same way that the 24 joules was calculated here, but we're losing, temperature's decreasing, so we're losing heat energy at this point, and that is the sum of the change in the internal energy and the work done on the system when it's being when it's compressing. We can trace the changes in energy, in the various forms of energy around this cycle. The first cycle, all 12 joules or 12.25 joules that go into the system contribute to the internal energy. So delta U01 is 12 joules. And that matches the delta Q, the energy that we put into the system, the 12 joules. Second, the energy put into the system is 24 joules, actually 23.05, using the approximations here though. The work done here is 6.6 joules, and the change in internal energy is 17 joules. Remember, the work done is the pressure times the change in the volume. The pressure is 110 kilopascals. Change in the volume is 0.6 liters, giving us 6.6 joules of energy. The remainder of the 24 joules, about 17 joules, is the change in internal energy. In the adiabatic expansion, as we saw in some detail, the work done is 4.1 joules, work done by the system against the pressure, the changing pressure, the adiabatically changing pressure. The change in internal energy is negative 4.1 joules, and of course that adds up to the delta Q, which is 0. And then in the final stage we have negative 10 joules of work, again 100 kilopascals and a loss of 0.1 liters. That's 110. 100 kilopascals, loss of 0.1 liters is a 10 joule loss, negative 10 joules of work done by the system. And the change in internal energy is negative 26 joules. Now, putting all that together, what's the total change in internal energy of the system as we go around this whole cycle? It's 0. So we have no change in internal energy. And if we look at this, we add 12 joules of internal energy and 17 here. That adds up to 29 joules. We lose 4.1 here, and we lose 10 internal energy. We lose 26 here. That actually adds up to 30.1. The difference between the 29 and the 30.1 goes into the approximations. If we do it precisely, it should come out 0, and I believe it does. And then the work done. We have no work done here. We have 6.6 joules here. We have 4.1 joules of work done here. That's a total of 10.7 joules. But then we lose 10 joules here. 10 joules of work is done on the system as it comes back to equilibrium, so that we have a net of approximately 0.7 joules of work that the system does. And notice that the potential energy change was 0.6 joules, which within round-off error is equal to that 0.7 joules, and we'll see if that really means anything.